Hello, everyone. Welcome or welcome back. Today, we are going to talk about autoencoders with respect to machine learning. We will see what are autoencoders, what is its functionality, its architecture, and we will end today's session with a Python example showing how autoencoders work. Okay, we will see a live demo. So, what is autoencoder? It is actually a type of neural network. Okay, it is a whole network itself with usage of or with the functionality for data compression and feature learning. It learns to encode the input data into smaller representation and then reconstruct it back. Okay, that is why it is also called as representation learning. Okay, it is automatically discovering the ways to represent the data. So think of it as like compressing it means, let's say if this is the image of an eye. So to compress it, we just draw an outline so that when we store this image as compared to this the sketch outline would be much smaller in size as compared to the original one, because the original one is much more detailed. If you can see, it has the eyeball color, it has the eyebrows and the other features that define the eye. But here it's just the outline. Okay, so this is compression. To store this image takes a little bit higher number of pixels as compared to this image. Okay, we'll see why we do this with some real life examples. So the flow is you have your original data, you pass it through the compressor or the encoder. After compression, what we get, the compressed data, is also called as either the latent space or it is also called as the bottleneck. And then we store it, and when we need the data again, we pass it to the decoder and we get the decompressed data or our data in our original form. So this is how the architecture looks like. You pass an input to the neural network. Now your encoder is nothing but a function, a mathematical function. Okay, some function that you decide depending upon what you intend to do with the input. Okay, if you want to compress the image or if you want to process the noise or what you want to do, depending upon that, your encoder will have a function to compress it, and your decoder will have a corresponding function to decompress it. Okay, compress or decompress. So the after compression, what you get is the bottleneck or the latent space. Okay, ideally x and x hat or inverse of x, it should be identical, but then sometimes there are what you call discrepancies in the original and the reconstructed one. Okay, that would be due to the loss functions. Now, thinking of it intuitively, think of it like if you have to store large what do you call amount of data, or let's say if you're traveling. Okay, you need to take a lot of clothes. What you do generally nowadays, what you it's available is like you fold your clothes nicely and then you have the suction pump thing where you suck it out and create a vacuum packing, and then so that you can fit more number of clothes, or more you can fit more clothes in the same amount of space, right? That's the goal. When you compress anything, you can store larger amount of data into smaller number of space. Or think of it like you're summarizing a long book into a shorter but still informative way. So the encoder, as we said, it processes the original image, uses a function, and compresses the output and gives a latent space. So H is our latent space or representation, and F could be any function which you decide. Okay. It could be what do you call any function that you have decided depending upon your input. Okay, your encoding function of your neural network, and the result H is the low dimension representation of the data. Okay. So something like, imagine taking a high resolution image and creating a smaller just thumbnail, when you see icons of a big image. So it just still just captures the essence of the image. And imagine the size of the icon as compared to the size of the original image. It's much, much more smaller. Okay. The encoder learns to identify the most important features or the patterns in the data. The decoder, reverse, right? That's why we encoded it. Okay. So the decoder is like a decompressor. Okay. It takes the low dimensional data or the representation and tries to reconstruct the original input. Okay. It learns to decode the compressed information. So it's like when you click on the thumbnail image, you actually get the original image back. Okay. Again, you pass the h, the latent space, pass it through a function, and you get the x hat, wherein x hat ideally should be equal or similar to or identical to the original input. Okay. What is a bottleneck? It's the key to an encoder. Okay, the bottleneck layer. It is actually after the decompression, whatever is created. Okay, it's called the bottleneck. Now, if the bottleneck is too large, the autoencoder might simply decide to learn the original input without learning its meaningful features. So if the neural network, if the autoencoder decides, oh, there is not much of a saving in compressing the data, then it will decide just to store it as the original image. Now, loss function, it's the loss, which means how different are or how different is the reconstructed image or reconstructed output with the original output, how different they are. Okay, so when we learn, I have explained mean squared error in one of my previous videos. Go ahead and watch it. Okay, if you're not sure about what is a loss function. What are the different types of autoencoders? You have the vanilla encoder that we just discussed, undercomplete, sparse, okay, denoising, variational, convolutional, lot of different types of autoencoders. Now, each different type of encoder will have different function for encoding and decoding. That's how what they are different, depending upon what use case they are for. Some real life applications where we can use autoencoders: image compression, noise reduction, which means clean up images, audios, or sensor readings, recommendation systems, anomaly detection, drug discovery, art generation, lot of real life applications which are available. All right, let's go ahead and see a code in action. So let me show you the code. Now this is a code to compress a data, okay? We pass an original input. We process the input. I just picked up some random image, a cat image. This is download and pre-process the image. Now we defined our autoencoder, okay, convolution, 2D layers. You pass the activation function, padding. You use the max pooling, which is 2D. Decoder, again, same convolutional 2D, sampling 2D, only 2 layers here, and you decoded it. But autoencoder, so this is your autoencoder and decoder. Now you build the autoencoder, and what we are printing out is the reconstructed image and the original image. So you would see the reconstructed image is just an outline of an original image. I will show you the output. It took a long time. I cannot run this program right now because it takes a long time for it to learn, go through all the 5 epochs, and then generate the output. So I have already generated the output. I'm just going to show you how it is. See, this was the original image, and this is after encoding. As you can see, it learned the outline and stores it. Okay, so this is the output of the encoder, the original image versus the encoded or the compressed image with just the outlines learned. Okay, so just going to close it. And now there is another program here which just shows the latent space. The output is the encoded data or the latent space. Very simple, takes a couple of seconds to execute. We have a sample data, just two-dimensional, and we define our latent dimension as just one. So we are compressing 2 dimensions into just 1 dimension. It's simple. It uses the Keras, and we are using TensorFlow NumPy for it. And now here, instead of ReLU, we are using linear activation function. You define your encoder model because, as we discussed earlier, this is nothing but autoencoders are nothing but a type of neural network. So it will have layers, it will have neurons, it will have everything. And we have kernel initializers means we just take some random values for height and bias. So here encoded data, so original data and encoded data. So let's run autoencoded and we'll see how we reduced 2D into one-dimensional image. So go here. So this was the here autoencoder. So this was our original data, which was 2D, and encoded data, which is reduced to one-dimensional. And this output here, what you see is the image compression, which was the output of the cat that I had shown. Okay, very simple. If you know understand the concept, again, just one last time, go through it. Used in a lot of use cases, as we saw, noise reduction, anomaly detection. So what we do is pass in the original image, um, pass it through a function, the encoder will encode it and store it. When we need the data back, we reconstruct it back using our decoder. But this encoder and decoder are related to each other, okay, or work hand in hand or in tandem, okay? So that's important to remember. All right, thank you all for joining. Feel free to like, subscribe, comment, whatever you feel like it, okay? Thank you all for your time. See you all again next time with some new fundas. MCP, yes. Stay tuned. All right. Thank you.